Hi. So in this lecture we are going to talk about the failures of the hydro turbine systems, primarily the failures caused by a process known as cavitation. So if you remember, there are different types of hydro turbine designs, but there are three designs that are most commonly used. What are these three designs? The first one is the Pelton wheel or Pelton turbine. The second one is the Francis turbine, where you have a turbine rotor, and then surrounding that there is a tube of water. The water flows inside a tube. So that is the Francis turbine. And the third one, which is a propeller, is known as the Kaplan turbine. So we have already discussed the different manufacturing processes that are used for making these different types of turbines. Now let's talk about what can go wrong. We know that different types of turbines will have different atmosphere where they are working, different environment where they are working. For example, if you compare your hydro turbines with a wind turbine, what's the difference there? The fluid is completely different. Not just that the fluid is different, one more thing is that the wind velocities can be very different at different time points. You know, sometimes you can have very turbulent winds, sometimes you can have no winds at all. But in the case of hydro turbine, you're pretty much controlling the flow rate of water. So that is one difference. Another difference is that in the water you will have dust, you will even have fish or small animals which will not be there in your wind turbine. No, that's not a problem there. What if I compare the hydro turbines with gas turbine or steam turbine? The temperature. Steam turbine operates at 600 degrees, or gas turbine operates at above 1500, but here we are working mainly at room temperature, water temperature. So there are different operation conditions, and that is why you also have different types of failures. So the mechanisms or the reasons for the failure in hydro turbines, so let's not call them failure, but something that causes damage to the blade of your turbine, which may ultimately lead to a failure. But what damages your turbine? There are four different processes known as cavitation, erosion, material defects, and fatigue, which can damage your blades. Now, what is cavitation? The process of cavitation is basically nothing but formation of bubbles in a liquid. Now, when do bubbles form in a liquid? There can be two things. Either the temperature is too high or high enough so that the liquid vaporizes, or the pressure is low. Even when the pressure is low, the liquid can vaporize and the bubbles can form. So I will quickly show you this process on the phase diagram. So let's say this is a single component phase diagram. Let's say it is for water. On y-axis we have the pressure, on x-axis we have the temperature. Okay, so now you see that there are these three different phases of the material that are shown here on the phase diagram: solid, liquid, and vapor. If I draw a line when your pressure is 1 atmosphere, temperature keeps on increasing, but the pressure is 1 atmosphere, then this point will be the melting point of the material. This point will be the boiling point of the material. So normal standard melting point and standard boiling point. Your liquid, let's say, belongs somewhere here. So between these these two circles in this region, your material should remain liquid. However, if the pressure drops, then it may not remain liquid. So you see that at the same temperature you can have bubble formation, and that is what is known as cavitation. And the point at which the cavitation starts is generally known as the flashing point. So what can this cavitation do? So we understand that, okay, in the turbine systems, why do we have, by the way, lower pressure of the liquid? Because the velocity is high. So simple Bernoulli's principle: if the velocity increases, pressure decreases. So it is possible to have bubbles, and in fact you may have seen these vortexes of bubbles. Bubbles can be in different, they can even take different geometries. Near the edges or near the vortexes, the row of bubbles can have different geometries. But how can that damage your turbine, the material of your turbine? Okay, so what happens when these bubbles are formed and they are also rapidly collapsed? So when the bubbles form and collapse, then there is pitting action onto the surface of the blade. Pitting means creating pits or holes onto the surface of the bubbles of your blades, and that is how it creates a type of erosion on the surface. So as such, cavitation is also a type of erosion, but since it is caused by bubbles and it's very specific to liquids, this does not happen in solids or gases. That is why it is given a different name. It's cavitation damage rather than erosion, but it is a type of, physically it's a type of erosion. So now there may be also small bubbles and there may be big bubbles, and this is for you to think and to find out whether small bubbles are more harmful or big bubbles are more harmful. So they will, remember, they will form and collapse, and that collapse, when it happens over a very long period and it happens continuously, then that can damage your surface by pitting. Now if there are cavities or these rows of bubbles between the guide vein blades or the runner, that can also reduce the overall cross section of the flow of the water. What does that mean? If there is, the cross section is reduced, then the discharge is also reduced, and that can lead to an imbalance in the efficiency of your turbine. Bubble collapse in general, even when they are not creating surface damage, when the bubbles collapse, they can lead to an overall efficiency reduction. And of course, because of the bubble formation and collapse, you will also, the flow becomes sort of unstable, which means the overall forces into your turbine systems can be uneven. So there's sort of turbulent flows here and there, localized turbulent flows that may lead to vibrations or oscillation of the overall turbine system, and when the entire machinery shakes or vibrates, that can further lead to damage or leakages in different parts of the turbine. Okay, vortex cavitation in the draft tube. So you know that Francis turbine, for example, has a tube. There is also a draft tube, the one from where the water comes out. When there are these vortex cavitations in the draft tube, then you can also, that can damage the tube, not just the turbine blades, but also the tube, and they can reduce the overall lifespan of the draft tube. Okay, so what do you think? Do you have this kind of cavitation also in Pelton wheels? Because generally Pelton wheels, you will operate at atmospheric pressure, but Francis and Kaplan will have definitely more probability, a higher probability of having these bubble vortexes inside the draft tubes, inside the casing. However, also in the case of Pelton wheels, there are some types of erosions happening. Generally, there are more silt erosions. We'll talk about that in the next lecture. However, when the flow between the jet and the bucket is unsteady, which could be due to any design or manufacturing faults, then that can lead to cavitation in the Pelton wheel. So if the wheel has not been designed properly, the splitting of the jet is not happening evenly, or if there is some manufacturing defect, maybe one side is heavier than the other, the Pelton wheel is not perfectly symmetric, for example. In that case, there may be some cavitation which can lead to damage of the Pelton wheel itself as well. However, it is this kind of problem is more common in Francis and Kaplan turbines. Okay, so well, what do we do to prevent this? In terms of manufacturing, the only thing we can do is to protect the surface using some sort of anti-erosion coating. So anti-erosion coatings not just for they are not just useful for the cavitation derived problems, but also for any kind of erosion. However, in the case of when you want to prevent your surface from cavitation, you will typically use elastomer coating. Elastomers such as PDMS or polyurethane and so on. So these elastomers can protect your surface from the damage that they experience by bubble bursting. However, in addition to manufacturing or design related issues, what we can also do is control the flow of the water. So what we need to do is the static pressure we should control, which should not fall below the vapor pressure of water. Now, how is that done? It is done using a lot of control valves. And other than that, what we can also do is we can take care of certain design aspects. So that there should be enough tip clearance so as to minimize the effect of bubble formation. To minimize the bubble formation, minimize also the effect of the cavitation, and that is how we can prevent the cavitation damage.